Bad tubes sometimes can be recovered. This is the documentation of the experience of a hobby project, made with the hope that it could be helpful to others. However, these videos are not intended as tutorials. They only show the development of a personal practice, which may or may not be a good one. Therefore, if you are following along, you are doing so at your own risk. Bad tubes can be a resource and should not be wasted. One may not be willing to deal with a bad tube right away, but in the meantime storing it is a good option. However, it is important to label a bad tube, not just with its code name, but also with the annotation of the reason for having put that tube aside. That would be very important later for deciding the fate of the tube. Vacuum tubes with a Bakelite base have the glass envelope glued to their base. However, over time the envelope might become loose. If and only if the tube is otherwise perfectly working, it is advisable to glue the glass envelope to the base. Here this is done using superglue. Vacuum tubes with a Bakelite base have their internal terminals soldered to those on the base. Over time, these soldered joints may fail. This is the tube type 75, which works well in the tried section, but one of the two signal diodes is not responding. The anode connected to pin 4 is not working at all. Pin 4 is desoldered, inspected, and then soldered again. Luckily, the tube is fully working again. When a tube rattles, that should not necessarily be a reason for discarding it. The loose material that makes the noise could just be trapped between the base and the glass envelope. And in this case, it is typically a piece of the original cement that went loose. This is not conductive, and it remains irrelevant for the functionality of the tube. If instead there is something loose inside the glass envelope, as long as that is not too big, so that there is no real concern for making a short, the tube might still be in a relatively good functional condition. If a tube problem cannot be resolved by just resoldering the pins, it may be useful to inspect the space between the glass envelope and the base. This requires desoldering carefully all the pins and then separating the base from the glass without breaking the envelope. However, separating the base from the envelope is easier said than done. If the base was recently reglued, that might be impossible. In this case, it is about a very old tube type 1H4 with the original cement that now has become almost ineffective. With great care, the glass and the base are turned a few degrees in the opposite direction, just enough to break the bond between them. The glass envelope might break in this process. Therefore, it is necessary to wear protective gloves and possibly also protective eyeglasses. Another thing to keep into account is that one must have a way later to identify each of the original terminals in order to be able to reinstall the base. Therefore, before touching the wires that come out from the glass envelope, one should draw a map of them, typically taking as a reference their position before and after the evacuation pipe. Also, the removal of the bakelite base of a metal tube should be possible following a similar procedure. Once the pins are all desoldered, the metal flaps that hold the base in position could be pried in order to release the base. However, one should consider that prying the metal flaps with too much force may break the bakelite base, and that tilting the base while extracting it might break the evacuation pipe. As for identifying the function of every wire terminal, it is sufficient to put a sign on the metal body of the tube. In order to be able to mount a bakelite base on a tube, one must have prepared a reliable map of the wire terminals coming out from the glass envelope. In this case, it is a tube type SQ7, where the grid is not involved with the base because it is connected to the top cap. With this type of base, it is necessary to prepare some extensions using thin copper wire. For soldering them to the original terminals, these extensions are prepared by making pigtail ends. The extensions with their pigtail end are then inserted in the wire terminals of the tube, where later are soldered. When all the extensions are in place, it is recommended to insulate the interval that goes from the glass to the pigtail joint included, using some colorful heat shrink pipe, so that every terminal can be easily recognized. The wire terminals, with the help of the extensions, can now be inserted in the corresponding pin of the base. This is a slow procedure that requires double and triple checking while doing it. Particular attention should be given to avoiding twisting the wire terminals together where they are not insulated, because that would result in a short circuit later. Also, the insertion of the wires in the correct pins should be carefully verified. This is why this phase of the process takes much more time than one could expect. When the wires are in the correct position, the extensions pulled out from the base pins are folded so that they cannot move while they are soldered. When a Bakelite tube base does not get loose, and it is still about the original cement that cannot be loosened with a solvent, the original base could be cut, replacing it later with a new one. Even though these clips appear at normal speed, they are edited. Therefore, one should know that the process is much slower than it is visible here. While it is relatively easy to cut the bottom of the base, which is off the end of the glass envelope, it is more delicate the removal of the residual ring around the glass. A very small triangular file is used here, paying attention that the file must never touch the glass. When a tube malfunction derives from an issue inside the glass envelope, there is usually no way to intervene. In this clip, which runs at half of the normal speed, the tube tester reports a short between one grid and the cathode. This is not recommended practice because it could damage the tube tester. However, testing the tube with the voltage that it is supposed to receive at the B+ line, some sparks are emitted and the short seems to be dissolved. It worked this time, but that was mostly luck. When a typical vacuum tube loses its seal and air enters the space that was meant to be vacuum instead, the getter compound becomes white, removing any doubt about it. However, in some occasions, the getter compound is not visible, maybe hiding under some shielding, or the gas might have been produced inside the tube itself, due to impurities, without becoming so much visible through the color alteration of the getter compound. Anyhow, one should know that the filament of a gas-poisoned tube might be still working, but usually without glowing as much as it should, and more importantly, drawing a greater amount of current. This is important to know because tubes with a white getter compound should not be tested on a typical tube tester, which could get damaged by the excessive current drawn from the filament of the tube under test. Gas contamination can be minimal under very low pressure conditions and then manifest itself as luminescence, as in this 80 rectifier tube when tested for emission. But this should not be confused with the glow of a regulator tube, which is supposed to contain traces of specific gas elements. When a tube is electrically unsalvageable for sure, like in the case of gas poisoning, clearly visible because the getter compound has become white if there is a separable base and or a top cap, they could be recovered. This particular tube, which has an octal base, was made with some technology inherited by metal tubes, and the removal of the base may be more difficult. If the tube suffered from gas poisoning, very likely there is a fracture in the glass envelope, making it more fragile, which means that it could break more easily while removing the base. If this is the case, like in this clip, it also takes more effort to remove all the residues remaining inside the base. If the base does not get loose, but there is no concern for the survival of the glass envelope, it is possible to hit on the base repeatedly until it gets released. A top cap of a glass tube can be removed by desoldering it, and if necessary by breaking the bond between the cement and the glass, turning it just 1 or 2 degrees. On a metal tube, recovering the top cap is a little bit more difficult, like the clip shows. Usually, metal ballasts are not in vacuum. However, they share the same types of bases, and it becomes natural to treat them or catalog them as if they were vacuum tubes. A metal ballast that is now open could be dismantled, and its space could be reused either for rebuilding it with the help of resistors or for hiding a smaller tube, which may be used as a replacement for an older and larger type. Anyhow, it is a good idea to keep the parts of a dead old metal ballast. When a tube is not usable anymore and nothing else could be recovered from it, but its glass envelope is still well sealed, it could be kept for making experiments, for exposition, or for art. In other words, before disposing of it, please consider donating it to someone else who could enjoy it in a different way.